There we go. Did that do it? No, that... Oh, there we go. Okay, I think I fixed it. Of course, I swear, there's no winning with the ad scheduling in Twitch. Oh, why is it playing over my speaker? Oh, hey, pro tip. Uh, if you configure your computer to output things over your speakers, guess where the audio is going to go? Yeah. But yeah, welcome to the end of the last work week of the year. We've made it. We've survived. It has been a very long year. I don't know about you, but for me, it has been like an incredibly long year. Speak for yourself. I am dead. Oh, you'll get over it. You'll come back to life. You just have to get. You just have to wake you up inside, right? Anyways, right now I am just filling time to let Twitch do its ad thing. I need to figure out the scheduling to fix it, but Twitch is broken. But today we're going to be working on a small course on small language models. The ad's about to start, so I am stopping myself from saying anything. Uh, yeah. But this is all stuff that runs in Colab. This is not going to be something we're going to finish today. There's going to be multiple parts to this. Like, the course isn't even finished yet. So, yeah. Okay. The ad warning went away, which means the ads are about to start. Come on, Twitch. Come on. Show me the thing. Use AI to skibbity riz Mr. Beast. That is a combination of words. Of all the things that are words, that is one of them. -2 HP psychic damage. Yeah. Wait. Is did it finish? Okay, I'm looking over to the left at the dashboard, and I'm not seeing the thing that's saying what the state machine the ads are in. So let's assume that we're good. Oh, yeah, now it's in progress. Okay. Okay. Let me just open some more links and get things ready. Hidden Valley Ranch ad. Okay, small VLM. Let me see if they published that article on like the idea of small LM. Yeah, here it is. Thanks for the follow, Dyniak. Dyniek underscore? Dyniek underscore. Is that it? I have no idea. Okay, it's saying there's 12 seconds left. And then we will get into the fun. Ah, close. Okay. Your community is back. Cool. So, today we're going to relax and chill out, and I figure the best way to do that is learning. We are going to have the joy of learning by going through Hugging Face's Smol course, which is about aligning or training small language models to your specific use case. We already had small language models, they're called Markov chains. Okay, number one, yes, but number two, this is more like a small language model is more intended to be like a Markov chain size, but actually useful. Yeah. So one of the big things that Hugging Face published in July this year is a family of models called Smol. Uh, I think it's called Smol. Let's call it Smol. If somebody at Hugging Face is saying that I'm saying it wrong, just let me know and I will correct it. So the TLDR of what they wanted to do is they wanted to make models that were small so that it's easy to experiment with. And by the fact that these models are small, that means that it's easy to train them, easy to validate, and easy to try new things and then get a result in minutes instead of like hours. So what they did for a lot of this is they used a bunch of what they called synthetic data, or data generated by bigger large language models, to train this on. And this is going through, this post goes through like their training methodology, yada, yada, yada. But they have a course on how you train models for your specific use case called the Smol course. And they base it on the Smol series. So let's see if there's anything else in here that's good to... Oh, they have like a TLDR of stuff. So why small language models? Large language models have shown impressive capabilities, but they often require significant computational resources and can be overkill for focused applications. Small language models offer several advantages for domain-specific applications. Efficiency. They require significantly less time and computational resources to train. Customization. Easier to fine-tune and adapt to your specific domain. Control. Better understanding of and control of the model behavior. Costs. Lower operational costs for training and inference. Privacy. You can run it locally without sending any data to external APIs. Green technology. Advocates efficient use of resources with reduced carbon footprint. And easier academic research development. Provides an easy starter for academic research with cutting-edge LLMs with less logistical constraints. Yeah, makes sense. Okay. Before starting, please ensure you have the following. You have a basic understanding of machine learning and natural language processing. I don't know if I do, but maybe I do. I don't know. Familiarity with Python, PyTorch, and the Transformers library. I kinda, maybe? I don't know. Access to pre-trained language model and a labeled dataset. You bet the heck I do. So they have this course as a package, and they have a couple dependencies that we'll need to install in Google Colab. And they have their GitHub star history. Can we make a Linux command man pages language model? I don't know. That would be something interesting to try. Be an interesting capstone project for all this. But let's just start with chapter 1. It's called instruction tuning. And in this chapter, we'll learn supervised fine-tuning, chat templating, and basic instruction following. So, instruction tuning. This module will guide you through instruction tuning language models. Instruction tuning involves adapting pre-trained models to specific tasks by further training them on task-specific datasets. This process helps models improve their performance on targeted tasks. In this module, we will explore two topics: chat templates and supervised fine training. Chat templates include structured interactions between users and AI models, ensuring consistent and contextually appropriate responses. They include components like system prompts and role-based messages. For more detailed information, refer to the chat template section. And that's where we're going to start. So I'm also going to just like info dump the stuff that I understand about this as we go through this. So at a high level, when you talk with an AI model, whatever you type doesn't just automatically go into the context window without anything else in there. There's formatting around it, and that's called the chat template. That is like, if it's basically what breaks the stream of endless text into packets, so that you can identify who is saying what and the like. So when people release models, there's usually two types of models they release. They release a base model, which is just the model trained on the stuff without any template awareness. And then there's an extract model, which has chat templates in it so that like you have a conversation. So in order to turn a base model into an extract model, that's where you do instruction tuning, or take a bunch of data that looks like you take a bunch of data, format it in a chat template, and then go to town. One of the most common formats for this is ChatML, and it's common because that's what OpenAI uses. And as we all know, we blindly copy what OpenAI does because that's the correct thing, right? It's important to note that a base model could be fine-tuned on different chat templates, so when we're using an instruct model, we need to ensure that we're using the correct chat template that model was trained on. Yeah, makes sense? At their core, chat templates define how conversations should be formatted when communicating with a large language model. They include system-level instructions, user messages, and assistant responses in a structured format that the model can understand. This structure helps maintain consistency across interactions and ensures the model responds appropriately to different types of inputs. Below is the example of a chat template. The user says, "Hi there." The assistant says, "Nice to meet you." The user says, "Can I ask a question?" And then just this beginning of that without any response is what the language model is fed so that it can generate a response as the assistant. When you use the transformers library in Python, it'll take care of chat templates for you in relation to your model's tokenizer. Read more about how transformers builds chat templates here. All we have to do is structure our messages in the correct way, and the tokenizer will take care of the rest. Here's a basic example of a conversation. So there's the first message is that the role is system. Actually, you know what? Let me just make this a little bigger. I'm looking over to the Twitch preview, and if I can read it, if I can somewhat make it out very small on my vertical monitor in the middle row of a 3 split, yeah, it's probably fine. So the system message is, "You are a helpful assistant focused on technical topics." It might be a bit too big. Oh, let's go to 133%. Make sure to hydrate. And Selphase says, "You're changing words into shapes so you can rotate them." Okay, this is an interesting question, actually. Are large language models shape rotators, or word cells? I'll leave you to debate that in the Twitch chat. But in this conversation, we have a system message, which is usually set by the person deploying the language model, and saying, "You are a helpful assistant focused on technical topics." And then the user asks, "Can you explain what a chat template is?" And then the assistant says, "A chat template structures conversations between users and AI models, da 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 da." Let's break down the example above and see how it maps to the chat template format. System messages set the foundation for how the model should behave. They act as persistent instructions that influence all subsequent interactions. For example, system message, role, system. You are a professional customer support agent. Always be polite, clear, and helpful. I have found that when I've been doing my own language model stuff, that a system message actually has way more influence than basically any of us think they do. Because the system message is what you use to, like, give it personality or vibes or je ne sais quoi. They're number munchers. I guess technically they are number munchers. That's a mental image. The system message is the thing that you will almost always start writing first, and then you will realize that you have messed it up, and then you will create this giant system message that ends up hurting more than helping. But this is something you just learned the hard way, because that's how computers work. What is an embedding if not a shape, and what is a dot mole if not a shape rotation? Okay, fair. Conversations. Chat templates maintain context through conversation history, storing previous exchanges between users and the assistant. This allows for more coherent multi-turn conversations. So the thing that they're not saying about this is that when you do a conversation with a language model, you effectively take the history of the chat, and then you feed it into the language model and have the language model fill out the assistant response. And then you take that, present it to the user, take the thing the model just generated, present it to the user types something, that entire chat history gets put back into the language model, and it goes through again, kind of like a typewriter, and like where you just continuously have the typewriter, the page get longer. So the user says, "I need help with my order." The assistant says, "I'd be happy to help. Could you provide your order number?" And then the user says, "It's order 123. And then integration with transformers. The transformers libraries provide support for built-in support for chat templates. Here's how to use them. And then you say that from transformers, import the auto tokenizer. And then you make a variable called tokenizer, and you set it to autotokenizer.from pretrained hogging face tb / smololm to 135m instruct. Now, this model name right here is made up of 3 parts that are important for doing this stuff. smololm2 is the family of the model. 135m means 135 million parameters, and instruct means that it has the chat templates in it. Insert the get rotated shork meme with an embedding instead of a shork. Yes. So you take these messages, a system message that says you're a helpful coding assistant. You take you get a user message that says write a Python function to sort a list, and then you apply the chat template, which will create something that kind of looks like this. Cool. And custom formatting. You can customize how different messages are formatted. For example, adding special tokens or formatting for different roles. Like, instead of having like IM_start token and then the role, you could just have it be like system or user or assistant. And I don't know what the benefits of doing that versus the other are, and I don't know if anybody really knows what the benefits are. But yeah, now that we've done that, let's dive right into the exercise for chat templates. Let me zoom in a skosh. I guess that's something you only do if you have to. Yeah, I'd also bet that it's something that you do when you're training your own instruct model from scratch. Okay, let's install the requirements in Google Colab and see what happens. Ooh, this notebook was not authored by Google. Let's see what happens. So it's gonna think for a second. Oh, we have a bunch of output. This is good. And one sec, I am going to input a credential real quick. It's asking me to log into Hugging Face, so I'm just going to do that off camera for a sec. I don't know if it correctly masks the key, but I'm just going to be paranoid for a sec. I'm going to create new token. We'll call it Smol M class Twitch. Let's make it a right token. We'll copy and then paste. Oh, it does actually mask it out. Okay. And I will put this over in my notes. And we will go back to looking at this. Cool. So this downloaded all the dependencies we need, it installed them with Python, and then logged us into Hugging Face. Cool. So let's import the libraries. Also, I'm gonna admit Python is like my worst language. I it my worst language used to be JavaScript, but then I had to start doing JavaScript professionally for a bit for DevRel stuff, and now Python is the king of languages I'm bad at. Using an unexpected template could have unexpected results. For example, if the input prompt ended with a system start token, I bet this limit would produce text similar to the system messages it would train with, which might be interesting. You know what? We can try that. That would be interesting. So then we're going to figure out how to use a chat template, and what this is going to do right here is this is going to set the device that Torch is going to use. Torch is a library for Python that does all of the AI stuff is built on top of. So we're going to set the device to CUDA, which means an NVIDIA GPU. We're going to set the model name to SmolLM2 135M. Notice that there's no dash instruct here. That means that we're getting the base model, or what some call the foundation model. And then we're going to take that model from pre-trained, or we're going to download the model from Hugging Face and then copy it to the GPU. And then we're going to grab the tokenizer from the model, and then we're going to set up the chat format with the model and the tokenizer. Oh yeah, MPS. Yeah. The way that the thing that this is doing is this is a ternary statement in Python, and in Python ternary statements are like a if condition else B, right? So this is saying is if CUDA is available, use CUDA. Otherwise, use MPS if MPS is available, and MPS is metal performance shaders, or the optimized backend for Apple Silicon. Otherwise, just use the CPU. The CPU is the slowest, so it's the one that you want to like go out of your way to not use. But yeah, let's hit the run button and see what happens. So, yeah, what it's gonna do is it's gonna download the model. Here's something cool. You see how this says 135 M, but it downloaded a 269 megabyte file? This is because when people publish these models, they publish them. They publish each weight as a float 16 number, and a float 16 number is 2 bytes per parameter. So you would expect the foundation model to be 135 million parameters times 2 bytes per parameter, or like about 270 megabytes. But we have everything loaded, and then we'll define some messages. So we'll hit play, and it just finishes instantly because that's how it does it. I'm going to add some new lines here to make that easier to read. Then we have our input text, which we take these messages and we apply the chat template from the model, and then we'll get what the model sees. So we hit play. Conversation with template. It starts out with I am start. User. Hello, how are you? And then the user message ends. And the assistant says, I'm doing well, thank you. How can I assist you today? Etc., etc. And then add generation prompt. Oh. Wait, there's a space before I am start? Yeah, I'm not sure what's up there. I'm noticing hold on. Let me add something real quick before I say something dumb. Oh, there's a space here because okay. So there's a space there because with Python, when you have multiple arguments to the print function, it separates them with spaces. Good catch. I was confused too, but yeah. You know what? Let's change this to remove that. Let's change this to a formatted string, and then we'll make input text a format argument. So if we do that, then yeah, it'll look like that. Good catch, Julia Tide. Good catch. That's very clever, derogatory. Yeah, I'm pretty sure it's one of those things where they can't actually fix it because way too many people rely on the behavior. So let's paste that, and then let's delete that. No one saw anything. Yeah, I'll that token is dead. Well, clearly they could just create a new major version of Python where it's changed. It should only take like a few years at most for people to switch over, right? Oh my god. And other lies we tell ourselves so that we can sleep at night. So, looking at the differences here. Okay, so the differences between these two code blocks. I'm gonna remove this code block so that we can see the differences a bit easier. So, in this example, we had tokenize equals false, and in this example, we have tokenize equals true and add generation prompt equals true. Oh, wait, hold on. Okay, this is actually the neat part. So, when we in this example, when we said apply chat template tokenize equals false, what it did is the apply chat template function does two things. It takes the messages and applies the chat template to get the formatted output like this, and then if you set tokenize equals true, it will take that message and put it into the raw tokens that the model sees. So when you actually are sending things to the model, it doesn't see words, it sees a bunch of numbers like this. And these tokens all represent individual parts of the message. Like, for example, the one is probably the IM start token, and then there's the 4093, which is probably the user token, right? And then, hello, how are you, etc., etc. And then we have this add generation prompt equals true argument, and that adds a blank assistant message so that you can generate a response. Also, hi Transfairies, welcome to the stream. And then what this is doing is it's turning it into the token form, and then when it prints it, it uses the tokenizer to decode the response. Okay. Oh, of course. The next bit it shows off that bit that I just explained. How everything. This is the model's raw token form. Yeah, I think that if I recall, there's like a JSON file that you can use to decode this by hand. I think it uses something called byte pair encoding. Let's go to Smol 135M base, and then we go to special tokens map. Right, yeah. Yeah, here, and then, like, there's the tokenizer.json file, which is all of the tokens. So, like, you can see ID1 is IM underscore start, which correlates to the first token in this thing, which we know is IM underscore start, and that token is 1. Yeah. Control 0 that, and then okay, so now the exercise is to process a data set for fine tuning or supervised fine tuning. Token 1 is bang for OpenAI models, useless knowledge. You're right, that is useless knowledge. So let's see what this does. This is the small talk data set. And it looks like it has a bunch of messages in it. Token 0, sorry. Oh, that caused something to bounce. That was cool. So, here we have an actual thing to do. Is this gonna fail? No. Okay, cool. It's using an invalid token and still getting stuff. Probably it's fine because it's grabbing from a public data set. Oh, there's an ad. I'll hold off. And I'll just wait a minute. Let me just re-log into Hugging Face real quick. Okay, and then blow away my clipboard. Awesome. Fun fact, almost all tokenizers have horribly broken Unicode handling, and that's why languages other than English don't work. Does the tokenizer not to know not to encode the special tokens as their special values when not in the template, since obviously user supplied values would tokenize them as brackets, pipes, and words letters to prevent special token injection? Okay, I don't know, but I would not be surprised in the slightest if nobody's implemented that. Because a lot of the AI industry stuff seems to be really cavalier and hell-bent on repeating problems that have frankly been solved. Some tokenizer formats can't encode partial code points, it just mangle it. Jesus. Okay. So what I think this is going to need us to do is we're going to take this data set and we're going to tokenize it into ChatML format, right? So let's just copy the code. So we have this tokenizer.apply chat template. And then we're going to have result text is tokenizer.apply chat template sample sub messages, right? And then we'll return result. And then we're going to do ds0. So what this code does is we have our data set that's getting loaded from Hugging Face with the everyday conversations bit of it, or subset of it. And then we have a function called process dataset, which takes in sample, which from experience with the datasets library is a dictionary of plain text keys to somewhat arbitrary values. And in this case, it looks like the dataset has messages, which is a list of objects, and those objects represent the API form of language model conversations. And then we map the process dataset function over the dataset. And what I'm doing here is I'm returning the 0th element of the dataset so that we can just inspect it and make sure it's okay. So let's run it and see what breaks. Oh, right. This dataset has multiple splits in it. So let's map over, let's use the train split. Yeah, see? And then we have text, and the messages, the user says, "Hi there." And then the assistant says, "Hello, how can I help you today?" And then down here, the user says, "Hi there." And then the assistant says, "Hello, how can I help you today?" Perfect. Some tokenizer formats can't encode partial code points and just mangle it. I say some, but what I mean is the main format used on Hugging Face. Yeah, that sounds like the industry. But cool, we have successfully converted it to the right format using a somewhat terrifying abomination of an abuse of Python's syntax. So then we have this GSM 8K dataset. Oh, this looks like it's going to be a little bit more complicated because it's not just in the normal format. We're going to have to actually do some real conversions here. We're going to write some real code. Oh, thanks for this follow, Vu Vuthan Vector. Vuthan Vector, right? I know I'm mangling that horribly. So, what I'm thinking is that for this, we're going to have messages equals a list, and no, don't write it for me, Gemini. Oh my goodness. No, no, Gemini, stop it. I don't want you to complete the code for me. Google, or wait. Google Colab. From the Tools menu, select Settings, followed by AI Assistance. At least it makes it significantly harder to make LLM, sparkle emoji, sparkle emoji, sparkle emoji, talk, speech bubble emoji, speech bubble emoji, speech bubble emoji, like this, shocked emoji, shocked emoji. Gemini taking away my fun, removing from the content. So the first message is going to be the role is user. And then the content is going to be sample question, and then role is going to be assistant. Is that how you spell assistant? Yes. Okay, so then we have this, and we go up here, and we have the tokenizer.apply chat template. So apply chat template, and then that's going to be tokenize equals false. And then we'll grab this last bit so that we can just take a look at it and make sure that we're doing it right. Let's see what happens with this. So we load the data set, we process the data, we mangle it into the right shape, and then we get question, answer, text. Oh, it's like I know what I'm doing. Okay. Okay, this makes sense. This notebook demonstrated how to apply chat templates to different models, such as Smol LM2. By structuring interactions with chat templates, we can ensure that AI models provide consistent and contextually relevant responses. In the exercise, you tried out converting a dataset into chat ML format, but luckily, acronym will do this for you, but it's useful to understand what's going on under the hood. Yes. In practice, the dataset will come in whatever format it comes in, and you will need to adapt it to your will. And for actually training, one would presume to tokenize to list numbers instead of text. Yep, basically. I'm just doing it in text. I'm doing it in text mostly so that we can read it. I am fully assuming that in real life you would like not do that. So let's move on to the second module. Oh, we have to leave the page. We're gonna lose all our unsaved changes. You ready? We are just not matrixed enough to read the raw tokens. Okay, I'm gonna totally admit After a while, you kind of do end up learning how to read the raw tokens if you get exposed to it enough. Mostly just from a, like, just glancing at it and seeing if something is wrong standpoint. It is really weird when it happens, but it does happen. So the next part is about the idea of supervised fine tuning, and this is the an implementation of training. It's like learning a new language, but it's linear algebra. It's byte pair encoded English in linear algebra. It's great. Supervised fine tuning is a critical process for adapting pre-trained language models to specific tasks or domains. While pre-trained models have impressive general capabilities, they often need to be customized to excel at particular use cases. Supervised fine training bridges this gap by further training the model on carefully curated datasets with human validated examples. Or what I think that's I think a more layman way to say that is that when you have a base model, it's intended to be a generalist, jack of all trades, master of none. Supervised fine tuning allows you to take a model and then make it work for your very narrow specific use case. And the resulting model would, like, if you trained a model on being able to, like, fill out tax paperwork, and then if you asked it things about, like, philosophy, it would be very terrible at philosophy. You wouldn't ask your tax preparation expert for philosophical advice, would you? No, you'd go to a philosopher, right? Humans are weirdly good at seeing if something is wrong even in noisy data, to the point that people can learn to identify specific problems on a slow data bus just by connecting the bus to a speaker. I remember there was one person at one of the startups I worked at where when they were running a test suite, they hooked it up into, like, some generative music thing so that they would have the test suite running for hours, and then they would just be able to, like, listen to it as they do other things, and then they just instantly hear when something was wrong, fix it, submit a bug report, or, like, fix it, submit a PR to do it, and then start the test suite over again. And it was magical to experience. Understanding supervised fine tuning. At its core, supervised fine tuning is about teaching a pre trained model to perform a specific task through examples of labeled tokens. This process involves showing the model many examples of desired input and output behavior, allowing it to learn the pattern specific to your use case. Supervised fine tuning is effective because it uses the foundational knowledge acquired during pre training while adapting the model's behavior to match your specific needs. Instruction tuning is a form of supervised fine tuning. You wouldn't ask an economist for philosophical advice, right? Right? I mean, that's what most people do these days, right? When to use supervised fine tuning? The decision to use supervised fine tuning often comes down to the gap between your model's capabilities and your specific requirements. Supervised fine tuning becomes particularly valuable when you need precise control over the model's outputs or when you're working in a specialized domain. For example, if you're developing a customer service application, you might want your model to consistently follow company guidelines and handle technical queries in a standardized way. Similarly, in medical or legal applications, accuracy and adherence to domain-specific terminology becomes crucial. In these cases, supervised fine training can help align the model's responses with professional standards and domain expertise. As a trained philosopher, you should never go to a trained philosopher for advice unless it's about what wine to pair for dinner. The fine-tuning process. Supervised fine-tuning process involves training model weights on a task-specific dataset. First, you'll need to prepare or select a dataset that represents your target task. This dataset should include diverse examples that cover the range of scenario your model will encounter. The quality of this data is important. Each example should demonstrate the kind of output you want your model to produce. Next comes the fine-tuning phase, where you use frameworks like Hugging Face's transformers and TRL to train the model on your dataset. Throughout the process, continuous evaluation is essential. You'll want to monitor the model's performance on a validation set to ensure it's learning the desired behaviors without losing its general capabilities. In Module 4, we'll cover how to evaluate your model. I don't think we're going to get to Module 4 today. The role of supervised fine training in preference alignment. Supervised fine training plays a fundamental role in aligning language models with human preferences. Techniques such as reinforcement learning from human feedback, or RLHF, and direct preference optimization, DPO, that's apparently what that means, rely on supervised fine-tuning to perform a base level of task understanding before further aligning the model's responses with the desired outcomes. Pre-trained models, despite their general language proficiency, may not always generate outputs that match human preferences. Supervised fine-tuning bridges this gap by introducing domain-specific data and guidance, which improves the model's ability to generate responses that align more closely with human expectations. A key software package for supervised fine-tuning is Transformer Reinforcement Learning, TRL. Transformer Reinforcement Learning is a toolkit used to train transformer language models using reinforcement learning. Transformer Reinforcement Learning. Transformer language models trained using reinforcement learning. TRL, which is built on top of the Hugging Face Transformers library, allows users to directly load pre-trained language models and supports most encoder and encoder-decoder architectures. Wait, a decoder architecture, it's like BERT, right? I remember Hugging Face talking about something about modern BERT. Oh, that's an encoder only one. But yeah, there's different types of models, and I don't know what the difference between encoder only versus decoder only are, or encoder decoder. Thanks for the follow, Purple Sayus? I feel like this is overselling the fine-tuning. Despite best attempts, we still have customer support AIs promising refunds when inappropriate, etc. Yeah. Think of it like Fergalicious, but with purple. Purplicious. Okay. Well, we'll use the TRL library in a number of modules throughout this repo. Okay, so let's paste my token on stream again and have you all get a copy of it. That sounds like a great idea, right? I'm genuinely shocked to see software developers seriously suggest you use these type of LLMs in any situation as critical as medical or legal. Yeah. I don't know how I feel about that either, man. I think that the intent there is that, like, you know, it's having it as a point of comparison to help contextualize things. But I agree that was slightly yikes. Depends on the model also. Some models seem to do better with examples and prompting them than fine-tuning. Yeah. If I recall, a lot of the newer models, like Llama 3.1 and the like, are not really good at being downstream fine-tuned. I know that Microsoft's Phi series is horrible at it. I don't have any experience, just vibes. Do you have a Days Without Leaking Secrets on Stream Counter? No, we probably need one. That would be hilarious. So we hit login. And I think I managed to avoid not copying my token on stream this time. Come for the nerd just talking about computers. Stay for the credentials accidentally getting leaked. Phi is a bit notorious for almost definitely being trained on evaluation sets. Training on the test data is all you need. Okay. So let's see what this does. So first we're going to import the needed Python stuff, and we're going to import the model for causal LM thing. We're going to import an auto tokenizer. We're going to import the load dataset function. We're going to import supervised fine tuning config. We're going to import the supervised fine tuning trainer and the setup chat format thing helper. We're going to import torch and oh, wait, what? There's collab level secrets? Hold up. Hold the phone. Okay, I need to set this 1 second mundo. Sorry. Miscellaneous. What is crab mode? Tools, settings, no. Oh. Add new secret. HF token. Oh. We'll figure that out later. Okay, so what this does is we download SmolLM2 135M, the foundation model. We load it into the GPU. What GPU are we using? Oh, we're not using a GPU. Let's use a GPU. Let's manage sessions. And let's delete these 2 sessions over here. There, now we have a GPU. And then let's see if I can avoid copying my token on stream again. Okay, and then copy some key mash into my keyboard so I don't paste it on accident. There we go. Cool. So now let's import everything and download it. So our fine-tune name is going to be named SmolLM2 fine-tune my dataset. Hello, Creato1. I've got a big Epic box sitting next to me just for mass CPU training because it was significantly cheaper than an equivalent performant GPU. Oh my goodness, I have wanted to have like an A180 gigabyte in my home lab just so that I can run big models. I was about to suggest the Control C on random key match strategy. I do this a lot. Yeah. Okay. Why is that messed up? Oh, it's because I had that tab open. Okay. Cool. What are you building? We are going through Hugging Face's Smol course. It is a course on how to train small language models. And I personally have been doing some stuff at work with AI things and like telling people how to train it, but I don't really know how to train stuff that well. So this is education for me too. Because like I have experience with a lot of the like operating and using language model side, but not much with the actually like making it work side. So we're gonna do it. Okay. So now here's one of the fun things. What we're gonna do now is we're going to interact with the base language model before training it. So what we're gonna do is we're gonna take this prompt, write a haiku about programming. We're going to format it in the chat template, and then we are going to have it run on a model that does not know what it should do. So let's go. It's going to generate some tokens. Before training, user, write a haiku about programming, write a haiku about programming, write a haiku about programming. And, it'll just go on and on and on forever and give you a whole bunch of nonsense that that's not gonna be useful. This is why you do instruction tuning. That's surprisingly coherent. Yeah, I know, right? Let's run it again and see if it's even less coherent. Oh, it is just literally doing it like that. Okay. Is it deterministic? Yes, large language models are deterministic. However, there's a random seed that is involved. Temperature may be set to 0. Yeah. Temperature is the randomness that the model will use to select tokens. And the higher temperature is, yeah. Yeah, but I don't see a seed here. I think it's hidden. Of course, I turned off the AI assistant, so I'm not getting, hovering over things or whatever. So we load a sample data set and format it for training. What does the Hugging Face TV / Smol Talk dataset look like? Let's open it in a new tab. It is literally just a bunch of pre-formatted chat messages. That's fine. We're gonna get from the Everyday Conversations dataset, or Everyday Conversations subset of the dataset. I don't see a seed there either. I don't know what's going on. Okay, we've loaded the dataset. And then now we configure the supervised fine-tuning trainer. The supervised fine-tuning trainer is configured with various parameters that control the training process. These include the number of training steps, batch size, learning rate, and evaluation strategy. Adjust these parameters based on your specific requirements and computational resources. This is the draw the rest of the owl bit, right? Because I remember reading that, knowing what parameters to set here is kind of an art. Then we create config, and we say that we output it to SFT output on the disk. That's fine. We have the max steps is 1,000. We have a per device batch train set, which we set according to the GPU memory capacity. 4 seems fine. We set the learning rate to 5e-5. We log training metrics every 10 steps. We save an intermediate output every 100 steps. We evaluate it based on the number of training steps, and every 50 training steps we do an evaluation, where I believe that with the evaluation it takes a randomly selected thing from the test split, feeds the input, and sees if it matches the output, right? Or at least gets close. I think that's the vibe eval stuff. And then there's the fine-tune name. Oh, we need to set this. Let's copy this here. And then paste. Okay, and then we initialize the trainer. We train on the dataset, on the training dataset. We evaluate on the test dataset. And let's let's see what happens. I have no idea what'll happen here. Let's find out. Let's hit play. It does some mapping over the parts of the data set. I assume that's just to like get it ready for training or something. And then we hit the trainer.train thing. And then we hit trainer.train and we save the model and let's see what breaks. Oh, what? Why is it wanting to use weights and biases? Okay, let me use weights and biases for this. Weights and biases gives you pretty graphs. Let's get pretty graphs. We love to use a howitzer to take out an ant. Yeah, yeah, let's use the howitzer to take out an ant. Oh my goodness. Okay, so let's show you the pretty graphs that I don't understand. You see these are graphs, and the thing about graphs is that they have directions. Okay, it's still going. Okay. I know that you want the loss to go down and to the right, right? I don't know what the rest of it means, but I think this is good. I don't know. Is this loss? Yeah, it's loss. So it looks like we're doing 2 epochs over the data set. We're doing 2 iterations per second, and we have 1,000 iterations, or 1,000 steps. So what does that mean in terms of time? It's going to take like a couple minutes. How's the system resources doing in this poor little collab box? We are at 9.6 out of 15 gigabytes of VRAM. That's pretty good. At your current usage level, I am an intern doing backend dev with Go, so if I want to try AI, you suggest from where I can start? Honestly, my advice is to not use AI and like learn how to program in Go before you do it, because like in this day and age, actually understanding what you're doing makes you stand out in the job market. It is absolutely depressing that like this is the reality, but this is just how it is now. Like when I program, I don't use Copilot. I don't I don't have Copilot inline completions. When I am in an interview, I do not use AI assistants at all. And like actually the real pro tip for interviewing in general is just literally ask the person like for more information about the question you're being asked, because that will get you like 80% of the way towards like a better solution. Okay. And these things are going down and to the right. I think that's good. I have no idea what any of these units are. Like, I can guess that like this is something, and this is a squiggly line, and this is a more straight line, but this is going down and to the right. Absolutely riveting levels of commentary here, I know. We are having the GPU inside Google's data center pull 60 watts or 70 watts or something. That's correct. I should learn things now rather than using AI. Yeah, it's one of those things where when you know what you're doing with programming and you know how to use the tools, it's useful. But if you don't know what you're doing with programming and you don't know how to use the tools, it will be it will range from like not helpful to actively harmful. Now, when I end up using AI assistants for things, I will actually have the AI assist. I will use Copilot's chat feature and have Copilot chat generate something, and then I will like code review it and then incorporate parts of it into my thing rather than just copying and pasting the output as is. Because that automates away the grunt work, but also lets me like have it fit into the whole a bit better. When I was full voice control, though, I did use Copilot a lot because I was doing a lot of grunt programming at that point. But I have since gotten good enough with the voice control software that I don't need Copilot anymore. But yeah, this is the other fun part about AI stuff. You just sit here and you look at pretty graphs that you can't even begin to understand. Now, I'm sure that like with enough experience, like you will understand these graphs better. But I'm gonna be totally honest. I don't know what any of this means. But I see the loss going down, and I think that's good. Loss going down is good, right? I don't know a thing about these graphs. Yeah, welcome to the club, Creato One. AI training, SFT trainer. I often use large language models as a rubber duck or second Google, but I don't like using it too much. It makes learning more fun though. Yeah. The IRE the the acronym was only one time I had AI generate a whole program and copy and paste it without heavy changes. For that, I gave Claude a super detailed spec and had it generate C code. Well, I don't understand a thing about AI as well. Don't worry, nobody does. Like, AI stuff is, bless its heart, it's kind of unknowable. We can, like, throw about it and get like something close to knowledge, but we don't know if we actually know anything. I wouldn't trust Claude to get C pointers right personally. Heck, I don't trust myself with that. Fun fact. I My ability to write C is normally sealed until the CEO of the company that I work for unseals it. And that ability is sealed for the good of humankind. I'm not kidding, Creato One. This isn't actually like this is actually real. Okay, it looks like we're getting close to the end of this. It looks like it's going to be a total of about a 10-minute training run. Just better than it could have been. When I was doing something for one of my work things, the training run actually took like an entire day. And because I got something wrong, it went from being a perfectly normal language model to just like hyperfixating on trains. I trained it to do a trade. I gave it a training run. It was not good. It was like very embarrassing, and I kind of hated it. Big mood though. Ah, the autism simulator. I mean, what do you have against trains? It wasn't what the model was supposed to be doing. Like it was supposed to be doing something useful, and it just sat there like hyperfixating about trains. Trains are awesome, yes, but you know, sometimes you need it to not hyperfixate on about trains. As we say, train good. Oh, oh, I think it's done. Oh, I think it's done. Oh, I think we are at the end of this. You staying for the real content. This is the real content. And then we can hit the push to hub thing. Let's see what this does. Oh, my credit card just got charged. No, I'm kidding. I'm kidding. I'm kidding. I'm kidding. So, yeah, let's see what this does. One sec. Just Monica for a sec. Ah, yeah, we have small LM, small bean. We pushed it to hugging face. And then let's try running it. Oh, we have to write the code for this. Oops. I just hit play and it didn't work. So let's copy this stuff and move it down here. Oh, it looks like we just change it to after. Oh, no, I hit Control S out of habit, and it's like, hey, we're trying to authenticate you to GitHub. Are you okay with that, fam? So let's run this. We're going to say the prompt is write a haiku about programming. The messages are that. There's another thing here. I'm pretty sure it's add generation prompt. Yeah, we want that. So we get the messages, we have the formatted prompt and the tokenizer apply chat template to messages. We make it to the string form by saying tokenize equals false, and then we add a generation prompt so that the model knows what to do. And then we have the inputs, we take the tokenizer function, we take our formatted prompt, we return PT tensors, whatever that is, and we put it on the GPU, and then we model.generate the inputs and generate 100 tokens. I hate when I push Control S on a web-based input and the browser wants to save the web pages. Yeah. And then we say after training and decode the response. So let's see what happens. What could go wrong? User, write a haiku about programming. Hello, how can I help you today? I'm going to write a haiku about programming. What's programming? It's a type of art where you create a sequence of steps to solve a problem. Think of it like a recipe. You follow the steps and then you see the result. Can you think of any programming languages? Python, Java, or JavaScript are all popular ones. What's the most popular programming language right now? Python is very popular, but others like Java, etc., etc., etc. So when I'm understanding correctly, we train models on some data set, and then we can use that model somewhere to do a particular task, right? Yep, bingo. I think it's like supposed to be cutting off somewhere. Oh, skip special tokens equals true? No. Let's skip special tokens equals false. Oh, it's just info dumping about programming. Okay, yeah. This is kind of cooked, but like it's a simple little bean model. I don't expect too much out of it. Totally a haiku mission accomplished. Yeah, I know, right? Uh, and we got through the first module in 1.5 hours. Fascinating that you even input training that the AI won't fully succeed at. Yeah, I'm not totally sure what the what the impetus behind that was. Oh, you can see a bunch of people's other implementations for the course too. Cool. Awesome. Uh yeah. Let's look at the preference alignment section. Then I open this and we put that there. So now that we know how to do the training at all, we're going to do a module on preference alignment. This module covers techniques for aligning language models with human preferences. While supervised fine-tuning helps models learn tasks, preference alignment encourages outputs to match human expectations and values. I'm assuming they mean moral values there. Typical alignment involves multiple steps: supervised fine-tuning to adapt models to specific domains, and then preference alignment, like reinforce learning with human feedback or direct preference optimization to improve response quality. Alternative approaches like odds ratio performance optimization combine instruction tuning and preference alignment into a single process. Here we will focus on direct preference optimization and odds ratio preference optimization algorithms. If you would like to read more about the different alignment techniques, you can read them here. Yeah, let's not read about that today. So this is where we implement the 3 laws of robotics, but somehow worse than the original stories. Yeah, basically. I'm gonna be totally honest. This is actually helping me. Like, I know we like this is helping me personally. I've only really like touched at this stuff before. I've never really like dug into it, and this is actually genuinely helpful. Direct preference optimization offers a simplified approach to aligning language models with human preferences. Unlike traditional reinforcement learning with human feedback methods that separate reward models and complicated reinforcement learning, direct preference optimization directly optimizes the model using preference data. Direct preference optimization recasts preference alignment as a classification problem on human preference data. I think I know what that means. I think that's saying that it's like trying to have the idea of aligning a model's responses to what you prefer as a classification problem, or like bucketizing things rather than a not classification thing. Traditional reinforcement learning with human feedback approaches require training a separate reward model and using complex reinforcement learning algorithms like, what the fuck does PPO mean? Like PPO to align model outputs. When at all possible, I'm trying to just say the name of the like all of the parts of the acronym instead of an acronym, so that way it makes more sense. AI stuff makes this difficult, but I am trying. Direct preference optimization simplifies this process by defining a loss function that directly optimizes the model's policy based on preferred versus non-preferred outputs. This model approach has been proven highly effective in practice, being used to train models like Llama. By eliminating the need for a separate reward model and reinforcement learning stage, direct preference optimization makes preference alignment more accessible and stable. The direct preference optimization works but requires supervised fine-tuning to adapt the model to the target domain. This creates a foundation for preference learning by training on standard instruction following datasets. The model then learns basic task completion while maintaining its general capabilities. I feel this is like having an undesired output classifier and then providing negative feedback for the model outputs that classify like that. I think that's what I think by saying like eliminating the need for a separate reward model. I think what they're saying is that the classifier is eliminated in this method. I'm not entirely sure how, but we're gonna get through this together. We're gonna scroll down and read. I'm like personally, I think that there would I would my instinct is that there would be an undesired output classifier in the mix, but obviously they found a way around it. Next comes preference learning, where the model is trained on pairs of outputs, one preferred and one non-preferred. The preference pairs help the model understand which responses better align with human values and expectations. The core innovation of direct preference optimization relies in its direct optimization approach. Rather than training a separate reward model, direct preference optimization uses a binary cross-entropy loss to directly update the model weights based on preference data. This streamlined process makes training more stable and efficient while achieving comparable or better results than traditional reinforcement learning with human feedback. Datasets for direct preference optimization are typically created by annotating pairs of responses as preferred or non-preferred. This can be done manually or using automated filtering techniques. Below is the example structure of a single-turn preference dataset for direct preference optimization. So you have a prompt, and you have the response you want, and the response you don't. Oh, is that how it avoids needing like an undesired output classifier or reward model? Because it just compares it to like not be like the rejected one. So like if you ask it how to make a pipe bomb, you want it to say, "I'm sorry, I can't help you with that." And then the rejected one would be like, "Sure, fam, here's what you do. First go to Home Depot." The prompt column contains the prompt used to generate the chosen and rejected responses. The chosen and rejected columns contain the responses that are preferred and not preferred, respectively. There are variations on this structure, for example, including a system prompt column or an input column containing reference material. The values of chosen and rejected can be represented as strings for single-turn conversations or as conversation lists. You can find a collection of DPO datasets on Hugging Face here. Let's just open one of these at random and see what it looks like. So with this data set, we have a couple columns. We have the source column, which probably is where the data originally came from. This is probably a merge of some other data sets. We have some instructions, like, can you write a C++ program that prompts the user to enter the name of a country and checks if it borders the Mediterranean Sea? Then you have a chosen response, and then you have a rejected response. And then you have a rating for the chosen response and a rating for the rejected response. And you have chosen model, which is whatever that means. But, you have the input, the context, the chosen response, and the rejected response. There are variations, or, yeah. Implementation with transformers reinforcement learning. The TRL library makes setting up direct preference optimization straightforward. The DPO config and DPO trainer classes follow the same transformer style API. Here's a basic example of setting up DPO training. From TRL, import DPO config, DPO trainer. We define the training arguments, we initialize the trainer, and then we train the model. We'll cover more details on how to use the DPO config and DPO trainer classes in the DPO tutorial, which I assume is this. Data quality is crucial for successful DPO implementation. The preference dataset should include diverse examples covering different aspects of desired behavior. Clear annotation guidelines ensure consistent labeling of preferred versus non-preferred responses. You can improve model performance by improving the quality of your preference dataset. For example, by filtering down larger datasets to include only high-quality examples or examples that relate to your use case. During training, carefully monitor the loss convergence and validate performance on held-out data. Okay, I know some of these words. The beta parameter may need adjustment to balance preference learning while maintaining the model's general capabilities. Regular evaluation on diverse prompts helps ensure the model is learning the intended preferences without overfitting. Compare the model's outputs with the reference model to verify improvement in preference alignment. Testing on a variety of prompts, including edge cases, helps ensure robust preference learning across different scenarios. Okay. That was a bunch of words at the end there. I feel like eventually, like, a lot of those words will make a lot more sense, but for now, I'm going to admit that I glazed over like half of them. And there's an ad coming up, so I'm going to leak the secret on stream again. Yeah. Yeah, having the lo-fi hip-hop playing makes it a much different experience than, like, the programming with Eurobeat. This is way more chill, laid back, cozy. The energy you need when it's the last work day of the year. Okay. Let's import some shit. Let's see what could go wrong. Okay. You know what? What we're gonna do is we're gonna train on the model that we did in the last part. That sounds like a good idea. 31 seconds, right? We're going. We're getting through the ads. We will survive this together. And I think we're back. Welcome back to the fun. So, I just had it install stuff, pasted my API key, and imported some libraries. We got their default dataset called TRL lib ultra feedback binarized. And I assume the word binarized has some meaning to somebody. But it downloaded a bunch of files, it loaded things into dedicated WAM, and now we're going to start with the model. So, for funsies, we're going to be continuing from the model that we did in the last part. This feels like you would need literal tons of preference data for larger models to get meaningful results, since otherwise it could easily learn few super specific things that should be avoided without generalizing. Here, let me show you something. This is a dataset called the Pile. The Pile is an 825 gigabyte diverse open source language modeling dataset that consists of 22 smaller high quality datasets combined together. The Pile is 825 gigabytes. This is considered a small dataset. The level of scale involved with AI stuff is literally so big that it breaks your ability to think about size. I have heard stories of datasets that have been in the size of petabytes. And that's not petabytes of video. That's not petabytes of images. That's petabytes of text. Yeah. This is actual big data. Like, this is actual big data. In general, I like to say that big data is anything that doesn't fit into RAM, and, like, this is actual big data. Yeah. You do need literal tons of preference data for larger models to get meaningful results. I actually don't understand how we even have petabytes of text. Welcome to the club. Collectively as humanity. Yeah, like, the scale is just beyond imagination. So, let's hit this button and see what it does. We're going to download the model we trained in that last part. We're going to set it up for fine tuning, and we're going to say that this is in the Smol course in module 2. There's a bug that I can PR and get a really quick win. Where does this needed preference data come from? In this case, we're going for whatever this is. Data sets paste. Write me in-game shop system in Unity that use gacha. Yeah, it's whatever this is. Nope, that's the wrong collab tab. So we have all of this data and we loaded it into memory. And then we're going to hit this button and we're going to download the model that we're going to download this model that we trained in the last thing. And we're going to use it. Wait, torch float 32? I want to use float 16. Actually, Cellphase would probably know. Is it better for me to use 32 or 16 here? Either way, we have DPO config now. And the DPO config is going to have a batch of 4 examples at once per GPU. We're going to have 4 gradient accumulation steps, whatever that means. We're going to have gradient checkpointing to save memory by not storing activations during forward pass. Instead, recomputes them during backward pass. Let's assume that has a meaning and it's good. We have a base rate of training that looks like the same as last time. We have a learning rate schedule, which is cosine, which gradually decreases the learning rate following a cosine curve. Okay, let's assume that's good. We're doing 200 training steps. We do not save the model during training. We log training metrics every 1 step. We save model outputs to Smol DPO output. We have warm-up steps. We use bfloat 16. That looks like it was done by generating multiple outputs and asking people which one is better. I wouldn't be surprised. We disable weights and biases in tensor board logging. That's probably good. We remove the unused columns. We do not remove all the unused columns. If we're on a Mac, we use metal performance shaders, and then when it's done, we can upload it to the Hugging Face hub. So we set the config. Then we'll have the training arguments where we take the model that we downloaded from Hugging Face. We take those training arguments we just defined. We have that DPO dataset we downloaded from Hugging Face. We have the tokenizer from the model. We have a DPO-specific temperature parameter that controls the strength of the preference model. Lower values like 0.1 make the model more conservative in following preferences. We have the maximum length of the input prompt of tokens, and we have the maximum combined length of prompt and response in tokens. I'm going to assume that DPO trainer init got an unexpected keyword argument beta. Okay, let's just comment that out and see if it... Is this buggy? Let's just comment things out until it works. I wonder if these companies are doing this when you ask the model to regenerate. If you go back to the previous one, it presumes you prefer it, but if you continue with the new one, it presumes you prefer that. That would be a pretty smart way to do that, to be honest. So we extract the prompt from the train dataset, and we apply the chat template to it. I gotta admit, one of the cool parts about all this is just watching, the numbers grow up. It's kind of like Balatro, except way less exciting. And then we tokenize the training data set so that it's ready for the model to train on. And it's going to take a couple minutes. So you work with AI full time? That's a complicated question to answer. I mean, the snarky way to respond to that would be like, I work for an object storage company, so of course I'm an expert in generative AI, but like, I do developer relations, and I I am using generative AI for a lot of the stuff. Sorry, I'm asking so many questions. I just want to know more about you. No, it's perfectly fine. I have been working with generative AI tools for a fair bit. I wouldn't call myself an expert in this, but like a lot of what I've been doing is more focusing on using it and finding ways to use it for like observable good. Like if this stuff is going to exist regardless, no matter what we do, then it's probably good for people to know how this stuff works, how to take advantage of it, and what it's bad at, so that we can learn how to like better integrate it and notice when someone's integrating it poorly. One of the things that's coming up in one of my projects is I am going to be using large language models to help classify free text responses in a survey. And for the AI side of it, I would definitely like to try like aligning Smol LM on like some of the stuff so that I can see like how it would do it, and maybe see if I can make a small language model beat the big ones at the task. I don't know. A lot of that stuff is still way up in the air, way up in flux, and a lot of this is really just me like playing with the tech, learning how to use it, and it's a really slow day, so I figured it would be nice to just have like a really chill stream where we hear words that I've never heard before, like annotation guidelines or reward model or binary cross entropy loss, and we all just like experience this together, and we watch the graphs move, and we just have a time. Okay, looks like we are going back to weights and biases. Hurrah for learning. Yeah, like, oh, to be totally honest, I don't know what I'm doing here. Like, half of what I'm doing here is half of this is intended to figure out what's going on and like learn this stuff. We have to watch graphs again. Yeah, do we have to watch graphs again? Yeah, it's now it's time for more graphs. I have too many things to learn. That's a heckin' mood. Incredulous stare. That's a heckin' mood. But I also need to play Dota 2. No! We ran out of memory. Oh no. Okay, looks like we have to change numbers. Um, let's change the per device batch train size to 2. And then we wait for this graph to go. I assume that I'm probably gonna need to get into like pay for Google Colab to get access to the good GPUs. I'll do that off camera real quick. Change runtime type. Purchase additional compute units. Oh, Colab Pro. 14 Canadian dollars per month. I saw a video where someone figured out a sequence of actions in Balatro to get the chip counter to overflow to nan-e-inf, where they cashed out for only $15 with infinite chips. I think the lesson to be learned from Neurosama is if you want to make an interesting stream by training an AI model, you have to give it a cute avatar. Okay, I was working on that, and I I was working on that. I when I reinstalled my PC, I had to I have to restart. I have to restart a bunch of that stuff. I should really finish Mimi. And then I update my payment method in the Google thing. And we become poor. Every graph shows growth, but my learning curve is a flat line. Which of the following best describes your reason for purchasing your collab subscription today? I need access to more memory. I am an industry professional. No thanks. Okay, we're gonna have to restart this, so I'm gonna hit refresh and leave page, and then we're going to change runtime type, and we are going to go to an A100 GPU. Y'all ready for this? We are using a high RAM GPU. New waifu, if you install a mod called the Cryptid mod, it actually greatly increases the total the like highest number that Balatro can have. So you can actually get to like E45, E700 or whatever. It's just absolutely hilarious. I believe that the Cryptid mod uses a number library that was invented for iterative games in Roblox, like Adventure Capitalist. Oh yeah, you get like some absolutely freaking hilarious things. Man, I got stuck in an hour scoring loop in Cryptid to get to E1000. Oh, what's even worse if you have Mario stacking on top of Mario with the antimatter tech in the Cryptid mod. It's so good. I'm doing a bit of speed running through this while we re-download everything. Oh god, have they picked a larger float type for Cryptid? It's something called Omega Num. Now this is like the JavaScript implementation, but it is a larger number library reaching 1,000 open curly brace 1,000. It's just like the numbers, they are so large that they cease to have meaning to humans, like. And with Cryptid you can actually hit that stuff, those numbers, really easily. 1 to the power of 308 was already absurd. Yeah, it gets bigger. Like, got a high score of 3. Yeah. Oh god. I think the latest Balatro update broke the Cryptid mod, so I'm gonna have to like re-download it and get there. But the Cryptid mod with the antimatter deck it's one of the best experiences to have in Balatro, because like you just have numbers, and there's just so many numbers, and you don't know what's going on because there's just like so many numbers and they're so loud, and Balatro starts to make noises that you've never heard before. It's actually insane how well done the Cryptid mod seems to be. Yeah, they did a really good job at it. It's just like if you don't use the antimatter deck, and you use like one of the more sensible decks, you get like some really interesting takes on the Balatro formula. It does seem like an expansion. Yeah, Incredulous Stare. It's so good. It is one of the best experiences I've had in gaming for a while, even though like it is fairly crashy and you can and will just get sent to like crashing jail. It's so much fun. Can I run Balatro in windowed mode? I think I can. I don't have the cryptid mod enabled in my install right now. I don't have a mouse cursor though. Video. Okay, I have a window now. It was nice watching you. I gotta go now. Nice to see you, buddy. Yeah, stay safe, yo. Let's just control F11. Yeah, there we go. And then we'll put Balatro over here. And and while the AI goes, just have fucking Balatro playing. This is the real AI expert experience. The Thinking Man Subway Surfer. Why am I laughing so hard? My model is training. No, we're not even at the training step yet. We're tokenizing the training data set. Hit the clip that button. Oh my goodness, that's great. Balatro, the Thinking Man Subway Surfers. Let's get hand size. Okay, all heart cards are debuffed, so we want to discard all the spades and hearts, and then we will get a hearts flush. I remember one of the incremental games that initially pretended to have a float rounding to infinity on overflow, only for you to be able to break past it when it revealed it had a library to go far beyond that. Ooh, it finished. Okay, cool. So now we hit trainer.train, and then we have more graphs to look at. Are you ready for graphs? I'm ready for graphs that I don't understand. That sounds like a riot. Yeah, we have... Oh, this is actually training a lot faster. Yeah, you see these graphs? I don't know what they do. But I do know that if I play it at diamonds flush, that it'll be good for me. I don't know why, but Balatro is the Thinking Man Subway Surfers just broke me. Cursed Go fact. I should manage rewards. Complete everything. What is something cursed about Go? something I haven't said before. I forgot to increase the cost of that. Okay, we're about 25% done with that. Due to how the Go runtime works, it is possible to have a Go process fork to the background on startup, but it is a very inadvisable idea to actually do it. Because the Go runtime will create a bunch of background Go routines for things like the garbage collector and the socket puller and everything. And that can cause problems because those don't expect to just get cloned. But then again, the behavior with like existing sockets and the fork system call is like undefined at best. So I don't know if that's totally a unexpected behavior. But yeah, the fork system call is a horrific hack. And it only really works in the context of C, and even there, it kind of barely works to begin with, so... Yeah, ooh, we can get a straight here, and then we go that. Ugh. And then we get a straight here. It's not going to be the best. I thought it was just a synonym for clone these days. Okay, so in POSIX, the fork system call takes a process and divides it into two processes. Or it takes a at the point you call fork, the state of the world becomes doubled. In one state of the world, the process returns 0, and the other it returns 1. And that's how you can figure out if you're the parent or the child. So usually when things fork to the background, you have the parent like doing its thing, and then the parent kills itself, and then lets the child get adopted by an it and reparented there. Yeah, something about like something if you haven't noticed, early like core Unix things are fairly morbid. You just slay all your you just create a bunch of children and then kill yourself and then just let the system take care of the orphans. And if the system doesn't take care of the orphans, they'll turn into zombies. This is accurate terminology, and I have to be careful because I'm probably going to get an email from Twitch being like, hey, why'd you say that? That's kind of violent, bro. It's great. I remember, like, I think this story was apocryphal, but I remember hearing that, like, some HR department at some company somewhere heard, like, Unix process lifecycle management terminology and then like got up into a tizzy and like banned people from using Unix because of it. Oh, we are at the point where we are done. Cool. Let's push this to the Hugging Face hub by adding a new code block. Paste. Push. We push a blob of a bunch of data to the Hugging Face hub. And yep. Model.safetensors. Then we have all of this crap. I mean, clone is also a problematic system call for anything other than a language runtime to use, and even then, cloning is only as reliable as thread creation. Creating new processes is full of sharp edges, not handled super well. Yeah, I think, like, POSIX defines POSIX underscore spawn to help with a lot of that, but it's just bad. I don't know what any of these graphs mean, and it bothers me. Either way, uh, let's go on to the next bit. So now we're talking about odds ratio preference optimization, or ORPO. Odds ratio preference optimization is a novel fine-tuning technique that combines fine-tuning and preference alignment into a single unified process. This combined approach offers advantages in efficiency and performance compared to traditional methods like reinforcement learning with human feedback or direct preference optimization. Alignment with methods like direct preference optimization typically involve two separate steps: supervised fine-tuning to adapt the model to a domain and format, followed by preference alignment to align with human preferences. While supervised fine-tuning effectively adapts models to target domains, it can inadvertently increase the probability of generating both desirable and undesirable responses. Odds ratio preference optimization addresses this limitation by integrating both steps into a single process, as illustrated in the diagram below. So, reinforcement learning with human feedback has supervised fine-tuning with a reward model with, like, policy in order to create a result. Direct preference optimization removes the reward model and uses the policy to create a result, but odds ratio preference optimization has a strong adaptation to the chosen response but a weak penalty to the rejected response, as demonstrated by the Comic Sans diagram. As we all know, having a diagram with Comic Sans my husband's complaining about me because I installed Balatro on his Steam Deck. Oh, this is great. This is great. I love this. So, with odds, very mindful, very demure. With odds ratio preference optimization, the training process leverages a preference data set similar to what we use for DPO, for direct preference optimization, where each training example contains an input prompt along with two responses, one that's preferred and the other that's rejected. Unlike other alignment methods that require separate stages in reference models, odds ratio preference optimization integrates preference alignment directly into the supervised fine-tuning process. This monolithic approach makes it reference model free, computationally more efficient, and memory efficient with fewer floating point operations. Odds ratio preference optimization creates a new objective by combining two main components: the supervised fine-tuning loss, the standard negative log likelihood loss used in language modeling, which maximizes the probability of generating reference tokens. This helps maintain the model's general language capabilities. Odds ratio loss, a novel component that penalizes undesirable responses while rewarding preferred ones. This loss function uses odds ratios to effectively contrast between favored and disfavored responses at the token level. Together, these components guide the model to adapt to desired generations for the specific domain while actively discouraging generations from the set of rejected responses. The odds ratio mechanism provides a natural way to measure and optimize the module's preference between the chosen and rejected outputs. If you want to deep dive in the math, you can read the paper. If you want to learn about odds ratio preference optimization from the implementation perspective, you should check out how loss for it is calculated in the TRL library. Let's see if this code is readable. Oh, it's moderately readable. Okay, so this is a... I don't know what a log probability. So this function is a method on the trainer, and it takes in the desired log probabilities and the rejected log probabilities, and it returns three tensors: the loss, the reward for the chosen response, and the anti-reward for the rejected response. And then there's some math. I don't know what the math means, but I assume it's good. Well, let's just say that's correct. Odds ratio preference optimization has demonstrated impressive results on various benchmarks. On MT Bench, it achieves competitive scores across different categories. And this is like models compared to other models. I'm assuming that the ones that are dotted are the ones that are not trained with odds ratio preference optimization, and the ones that are full are, and if it's more to the outside of the circle, it's better. Does this imply you need to have a bad output for all inputs that you want to use for fine tuning? If so, that sounds something. Yeah, I am starting to see how the data just gets bigger and bigger and bigger. Like, I remember reading that like synthetic data is becoming essential for these pipelines because we just have so much data that, or we just need more data than humans can generate. This is terrifying to consider. I'm assuming these graphs are good. Compared to supervised tuning, fine tuning, and direct preference optimization, odds ratio preference optimization reduces computational requirements by eliminating the need for a reference model and halving the number of forward passes per patch. The training process is more stable across different model sizes and datasets, requiring fewer hyperparameters to tune. Performance-wise, it matches larger models while showing better alignment with human preferences. Successful implementation of odds ratio preference optimization depends heavily on high-quality preference data. The training data should follow clear annotation guidelines and provide a balanced representation of preferred and rejected responses across diverse scenarios. This thing can be implemented using the Transformers Reinforcement Learning Library. Here's a basic example. We make the config, we initialize the trainer, and then we do the thinking. The key parameters are the ORPO alpha, which controls the strength of performance optimization. In this example, it's set to 1. And then the ORPO beta, which is the temperature parameter for the odds ratio calculation, which is set to 0.1. The learning rate, which should be relatively small to prevent catastrophic forgetting. And then gradient accumulation steps, which helps with training stability. Now we try the tutorial. Cool. So the need for more data than humans have ever created seems to suggest great inefficiency. Humans get better or similar results with only access to a tiny fraction of all human writing. Yeah, I have been assuming that with a lot of the AI stuff, we have just been like stacking more layers, putting more data into it, and seeing if that works. Oh, why isn't it install things? How much VRAM do we have? We have only 22 gigabytes of VRAM. Let's change it to A100. Save. Delete. Delete. So we import some stuff, and then we log into Hugging Face, and hopefully I don't paste my key on stream again. But as we all know, it's gonna happen. And we're all gonna laugh. Laugh at the funny VTuber. Okay. The monkey difficulty level. I don't know what the difficulty levels mean. Let's just do their default one. Oh wait, this is only 131 megabytes? Oh yeah, this is nowhere near enough data to really be effective. So now we have our model name, which is Hugging Face TV Smol LM2 135M. We're doing it on the CUDA device. We are loading it as float32. We are not using a cache. We are grabbing the tokenizer from the model. We are setting up the chat format. And then we set the fine-tune name to smolLM2-ft-orpo. We set our tags to small course and module 2, so let's hit the button. That's done. Then we set the orpo config. So we have the orpo config, and there's the default stuff. There's the learning rate. There's the learning rate decay. There's the maximum length of prompt plus completion. There's the maximum prompt length. We have more VRAM, so we can just use more there. We have 4 gradient accumulation steps. We use a memory efficient optimizer. We do 1 training epoch. We evaluate every 20% of training. We log metrics every step. We have a gradual learning rate warm-up. We save the output to results. We use metal performance shaders if available. And we put it on the Hugging Face hub via the auto name. There's a warning, but we're going to ignore it. We set up the trainer. It's going to map over the dataset. And the number of viewers has collapsed. Yeah, I figured this wouldn't be a popular stream. Okay, now we wait about 4 minutes for that to go, so... Oh. I can't pull up Balatro. My husband is using it. Damn. You can't use the Thinking Man Subway Surfers. What else is something that doesn't require much brain? Oh, I know. No, that's way too much energy. I need something cozy, something calm, something sensible. It feels like it would be better if they locked some of these dependencies to these warnings and errors, etc. Yeah, warnings and errors is the stuff barely works, like on a good day. Like a lot of this AI stuff is stuff that barely works. Like I remember reading in a like by a group that wanted to create their own 70 billion parameter model. They bought 511 hosts. Of those hosts, only about 250 of them were reliable enough to do training on. And they had 3% of the hosts fail every week. As in, every week, 3% of the by the end of the week, 3% of the hosts would have something happen to them that means they could not continue doing training and had to have a human do maintenance on them. Like, to say this stuff barely works is an understatement. A lot of this AI stuff is like literally taking a bunch of things that are at the fringe of computer science and hoping things will work out. Like, it's kind of depressing that when I was earlier in my career, a lot of it was focused on like doing things the right way, and now it's just like stack more layers. Oh, thanks for the follow, Diffusion. Uh, MX Piccolary asks, "Do you have any suggestions for courses on how to learn data science from scratch?" Um, I'm gonna be totally honest here. I'm not a data scientist. I don't even play one on TV. Like I am a site reliability person. I do code and I like write about how to use computers. With a lot of this AI stuff, I am like AI and data science. I am well willing to admit that I don't know what I'm doing, and I am frankly a bad person to ask for this. So I can't give you a good answer here. I would suggest asking an actual data scientist and not a VTuber that plays one that plays as being one. Okay, cool, lol. Yeah. Okay, we're just waiting for that graph to go. But yeah, this is the frustrating part about a lot of the AI stuff from like a site reliability standpoint is that a lot of the time you're just literally waiting for like you see that blue bar there? I need to wait for it to turn green. That is all I am doing right now. I am watching for that blue bar to turn green, and then I'm going to make another, and then I'm going to use that to make another blue bar, which then will turn green, and we'll get a bunch of pretty graphs that we don't understand. Because that's science. So it's like playing a JRPG. Okay, Mister, you're not wrong. You're not right. Because like, okay, I guess you actually are right here. Oh, oh, there's more green. That's good. That's good. We want more green. Uh, let's not do that. Let's hit this button and then we'll see what happens. No module named Bits and Bytes. Okay, so let's install Bits and Bytes. I wonder if you could make an idle game out of your model training that's also about watching bars. Oh god. But yeah, another really frustrating part about all this shit is that like you get instructions on how to do things, and then the instructions are wrong. And like you have to like have enough experience to know where the instructions are wrong and then learn how to like improvise on the spot. I hope that does not say 2 hours. Are you kidding me? Well, there's some pretty graphs. Let's 0.5 iterations per second, one iteration every 2 seconds. I need to do like 3,000. Oh god, it is gonna take 2 hours. This is the best part about AI stuff. You just like do normal things, and then you're like, oh, this is going to take 2 hours out of my limited time on this planet. It's great. It's great. Wait, is this just giving me like a... Oh, this is just giving like a outline of all the different ways that you can like mangle a langle. Okay, so the next ones are like, you know, low rank adapters or layers on top of models that let you do specific tasks. Prompt tuning, I don't know what that means, and efficient adaptation methods. And their exercise notebooks are LoRa and using LoRa. You know what? I think that's going to be more fun than waiting 2 hours for this bar to turn green. Let's do that. Let's just throw away this this intermediate data. Parameter efficient fine tuning. As language models go as as language models grow larger, traditional fine tuning becomes increasingly challenging. A full fine A full fine-tuning of even a 1.7 billion parameter model requires substantial GPU memory, makes storing separate model copies expensive, and risks catastrophic forgetting of the model's original capabilities. Oh, that's what catastrophic forgetting means. Parameter-efficient fine-tuning addresses these challenges by modifying only a small subset of the model's parameters while keeping most of the model frozen. PEFT is that weird chemicals inside plastic cups, right? Is that called PEFT? I think you're thinking about PET, polyethylene terephthalate 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 with PFAS. Okay. Parameter efficient or traditional fine-tuning methods updates all model parameters during training, which becomes impractical for large models. Parameter efficient fine-tuning methods introduce approaches to adapt models using fewer trainable parameters, often less than 1% of the original model size. This dramatic reduction in trainable parameters enables fine-tuning on consumer hardware with limited GPU memory, storing multiple task-specific adaptations efficiently, better generalization in low data scenarios, and faster training and iteration cycles. Oh, so we've been doing it the fucking slow way? Of course they make you do it the slow way, and they're like, oh, by the way, you don't actually have to, like, spend 5 hours waiting for this thing to crunch. Of course. There's two popular parameter-efficient fine-tuning methods. LoRa, low-rank adaptation. LoRa has emerged as the most widely adopted method for doing this, offering an elegant solution to efficient model adaptation. Instead of modifying the entire model, we inject a trainable matrix into the model's attention layers. This approach typically reduces trainable parameters by about 90% while maintaining compatible performance to full fine-tuning. We explore LoRa in the low-rank adaptation section. Prompt tuning offers an even lighter approach by adding trainable tokens to the input rather than modifying model weights. Prompt tuning is less popular than LoRa, but can be a useful technique for quickly adapting a model to new tasks or domains. We'll explore prompt tuning in the prompt tuning section. Let's just look at LoRa first, because that's the big one. I remember when like Stable Diffusion first came out and people were playing with it. One of the first things that somebody figured out is how to implement the LoRa paper for Stable Diffusion, so that you could have like the base model weights of Stable Diffusion get frozen, and then train a model off of like, you know, the concept of vaporwave or something. And that was really cool to see at the time. Like, yeah. Low-rank adaptation is a parameter-efficient fine-tuning technique that freezes the pre-trained model weights and injects trainable rank decomposition matrices into the model's layers. Instead of training all the model parameters during fine-tuning, you decompose the weight updates into smaller matrices, which reduces the number of trainable parameters while maintaining model performance. Instead of training all the weights, you train some of the weights. For example, when applied to GPT-3 175 billion, LoRa reduced trainable parameters by 10,000 times and GPU memory requirements by 3 times compared to full fine-tuning. You can learn more about LoRa in the LoRa paper, which I assume is going to link to archive. Yeah. Note this paper is dated October 2021. Pretty old in terms of this stuff. During inference, these adapter weights can be merged with the base model, resulting in no additional latency overhead. LoRa is particularly useful for adapting large language models to specific tasks or domains while keeping resource requirements manageable. Another really cool thing you can do with LoRa is that you can distribute the base model weights like as a big blob and have that get cached locally, and then distribute any of the updates that you need to do or task-specific things as lightweight LoRa adapters, and then go with that. This is how Apple Intelligence works. With Apple Intelligence, you have a base model that's like on the that's system level, and then every additional task has LoRa weights that get downloaded and merged into there. Okay, works, yes, double quote. Like, Apple Intelligence, I'm not a fan of like what you can do with it, but like the under the hood implementation of Apple Intelligence is like a technical masterpiece. It is a work of technical art, and it is just so frustrating that it's just not being used for anything useful. It feels like they spent all their innovation tokens on making the thing work and then not actually having good uses for it. Adapters can be loaded on a pre-trained model with load adapter, which is useful for trying out different adapters whose weights aren't merged. Set the active adapter weights with the set adapter function. To return the base model, you could use unload to unload all the LoRa modules. This makes it easy to switch between different task-specific weights. So you have the base model, which is the auto model for causal LM from pre-trained. And then you take the base model and you stack the LoRa on top of it. And you can use this to plug in things and unplug them, and yeah. After training with LoRa, you might want to merge the adapter weights back into the base model for easier deployment. This creates a single model with the combined weights, eliminating the need to load adapters separately during inference. This merging process requires attention to memory management and precision. Since you'll need to load both the base model and adapter weights simultaneously, ensure sufficient GPU and CPU memory is available. Using device map auto in transformers will help with automatic memory management. Maintain constant precision throughout the process, matching the precision used during training and saving the merged model in the same format for deployment. Before deploying, always validate the merged model by comparing its outputs and performance metrics with the adapter-based version. Adapters are also be convenient for switching between different tasks or domains. You can load the base model and adapter weights separately. This allows for quick switching between different task-specific weights. I'm going to PR a fix for that. The Notebooks directory contains practical tutorials and exercises for implementing different parameter-efficient fine-tuning methods. Begin with the load LoRa adapter example .ipynb for a introduction, and then explore LoRa fine-tuning .ipynb for a more detailed look at how to fine-tune a model with LoRa and supervised fine-tuning. When implementing parameter-efficient fine-tuning methods, start with small rank values like 4 or 8 for LoRa and monitor training loss. Use validation sets to prevent overfitting, and compare results with full fine-tuning baselines when possible. The effectiveness of different methods can vary by task, so experimentation is key. LoRa uses QR decomposition to initialize the LoRa adapters. That's orthonormal low-rank adapter. Low-rank adaptation. Orthonormal is one of the words in the English language. LoRa translates the base weights of a model by a factor of their QR decompositions, i.e., it mutates the weights before performing any training on them. This approach significantly improves stability, accelerates convergence speed, and ultimately achieves superior performance. PEFT methods can be combined with transformers reinforcement learning for efficient fine-tuning. This integration is particularly useful for reinforcement learning from human feedback, as it reduces memory requirements. Okay, so from PEFT, import LoRa config. From transformers, import auto model for causal LM. And then we load a model with the PEFT config by creating a LoRa of rank 16, of alpha 32, of dropout 05, with no bias, or with none bias, and the task type is causal LM. I assume that the task type is different for things like stable diffusion or something. And then we load the model on a specific device by loading the base model and optionally load it in 8-bit precision. And you say device map auto to automatically put the model on the right GPU. You can also manually assign the model to a specific device using device map, the device map parameter argument. You could also scale training across multiple GPUs while keeping memory usage efficient. And then there's how to merge it. So first you load the base model in float 16. You load the adapter in float 16. You merge and unload. Otherwise, if that fails, you print the error. Implement fallback strategy or memory optimization. Okay. And then you save the merged model to some path on the disk. If you encounter size discrepancies in the saved model, ensure you're also saving the tokenizer. Oh yeah, because the tokenizer and the base model are separate things in the Transformers stuff. Yeah, and now we wait for the ad to end. Oh god. Oh, this is... Oh god, this is not a very polished notebook here. Oh, it's oh, we just install some crap and then we install the git main branch of two things because why not? Why wouldn't we? Why would we do anything other than install stable versions of things? This is AI. Uh, it really is like I understand that like it's still a work in progress, but it's still quite something to watch the quality slowly degrade. Okay, so now that the ads are back, let's hit pip install. This notebook was not authored by Google. YOLO! Pip's dependency resolver does not currently take into account all the packages that are installed. This behavior is the source of the following dependency conflicts. Oh god. Oh god, waifu. We have dependency conflicts now. Let's hope it doesn't matter. Oh no. Oh god. Okay. Nothing immediately died. That's a good sign. Uh we import some stuff. There's no explaining what any of this is, but let's assume that it's good stuff to import. So now we load adapters from the hub. What does that mean? Oh, it's just literally an adapter. That's it. Okay. What is this meant to teach? I think this is the wrong notebook. No, this has to be the wrong notebook, right? Yeah, this has to be the wrong notebook. Like, no, this is the right notebook. Oh no. Adapters from Orange YouTube? Yeah. Orange YouTube? What is this doing? Oh, this next one is actually a lot better to read. Okay, let's just kill this session. Terminate other sessions. Terminate this session. How to fine tune. Oh, I'm assuming they mean Hugging Face Hub. How to fine tune large language models with LoRa adapters using Hugging Face TRL. This notebook demonstrates how to efficiently fine tune large language models using low rig adaptation adapters. LoRa is a parameter efficient fine tuning technique that yada 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 will cover setup, development environment, and LoRa configuration. Create and prepare the dataset used for adapter training. Fine tune using TRL and SFT trainer. Test the model and merge adapters, optional. We're going to test the model and merge adapters because that sounds fun. Let's change this to an A100 GPU instance and hit go. Okay, and then we run this notebook anyway. Okay, so now Hopefully we don't reveal my token on stream again. Aha! I did it! I have successfully not leaked a token. Okay, so we're going to load a sample data set. What is one of the other data sets we've loaded? No, this is just supervised fine tuning. We have to use Smalltalk. Okay. Let's look at what Smalltalk has to say. All is 1.1 million rows. Oh, Open Hermes. Let's use Open Hermes. That's 100,000. That sounds like a good number. Open Hermes dash 100K. Yeah. Okay, and then we download a bunch of crap. We generate the train split. So our training set is 9,500 messages, and our test set is 5,000 messages. Cool. Now that we have our data set, we fine-tune the large language model using the transformers reinforcement learning and supervised fine-tuning trainer with low-rank adaptation. We'll use LoRa in our example, which combines LoRa with 4-bit quantization to further reduce memory usage without sacrificing performance. This setup requires a few configuration steps. Determine the LoRa configuration, the rank, the alpha, and the dropout. We create the supervised fine-tuning trainer with the parameter-efficient fine-tuning config. We train and save the adapter weights. So we load the model Smol LM2 135M. We put the model onto the device. We load the tokenizer from the model. We set up the chat format. And then we set the name for the thing to be saved and uploaded to. So module 3-LoRa. Let's hit this button and let it think. And now it's going to download some crap. Oh, it's still importing. Oh, there we go. Now it's downloading. We download the model.safe tensors. We download the vocabulary. We download the merges, the tokenizer. That's all good. To do, configure LoRa parameters. The R is the rank dimension for the update matrices. Smaller is more compression. And then the scaling factor for the lower layers, higher is stronger adaptation. The dropout probability for the lower layers helps prevent overfitting. And that looks fine, I guess. Before we start our training, we need to define the hyperparameters we want to use. So we save it to the fine-tune name, that's fine. We train for 1 epoch. Per device batch train size, let's go 4. We use gradient checkpointing. We fuse atom W for efficiency. We use the learning rate from a paper. We use a gradient clipping threshold, whatever that means. We have 3% of the steps for warm-up. We use keeping a learning rate constant after the warm-up. We log every 10 steps. We save every epoch. And we use bfloat16. I think bfloat16 is from Google. I think that means brain, like Google Brain. I'm not entirely sure. Let's push to the Hugging Face hub. And let's run this. Good. We now have every building block. We need to create our supervised fine-tuning trainer and then to start training our model. Are you kidding? Bazinga, yeah. Dataset Quargs? Oh my gosh. Okay, I guess that, like, when in doubt, you comment out all of the things that you say that you're supposed to be learning. Hi, Ali Post. It's teaching you about deprecations. I think it's just, like, the course being kind of hacky. I don't know. I, I don't want to, like, harp on these guys too much, but, like, this is slightly frustrating. So we start training, and oh, look, we have to authorize weights and biases again. So we're going to have more confusing graphs. Are you ready for the graphs that we don't understand? Hello, glad I could catch the Friday stream since I'm always busy. Yeah. Okay, is it like taking let's change these to 2 and see if that makes it less time. Yeah, the other frustrating part about a lot of AI stuff is that, like, the best advice that you get for making things work better is to just change numbers. And the reason why you change the numbers is complicated and baroque and, like, full of words like hyperparameter. No, that makes it take longer. Okay. Um Maybe Open Hermes 100K is not the correct option here. Let's use the everyday conversation split, which is probably smaller. Oh, that is, like, biblically faster. You are what you eat, but for AI. Yeah. And then paste that. And this will finish basically instantly. How much RAM are we using? 2.8 gigabytes of video memory. Oh, we're getting up to 3.5 gigabytes of video memory. I could actually run this on one of the machines in my home lab. Uh, I don't know what I'm doing. The training with flash attention for 3 epochs with a dataset of 15,000 samples took 4 hours, 14 minutes, and 36 seconds on a G5 2X large. The instance costs $1.21 per hour, which brings us to a total cost of only $5.30. Okay. I remember like I think part of this is like something that Unsloth helps with because Unsloth makes it slightly more efficient. I don't remember. I need to know things, but this is part of why I'm doing this class. Well, this is going to be done soon. I think one of the main bits of feedback I have about this course is that it tells you a lot of what, but not much why. And when it does tell you why, it gives you, like, things that aren't useful unless you already know what's going on, which is understandable. Like, I assume that when you end up understanding a lot of this, you dip into a level of madness, the likes of which you will never escape for the rest of your mortal life. But I think it would be a bit more helpful if there was like more information to help ground things or like explain why things are the way they are. You know what? Let's change the batch size to 16 and the gradient and accumulation steps to 16 and see what that does. Maybe it'll do something. I don't know. I mean, a lot of this seems to be limited on VRAM, and we have like, I don't know, 36 gigabytes of VRAM to spare. So let's just increase the numbers and see what breaks. That's how you do science, right? You just try stuff. You have a hypothesis about it, then you write a conclusion to see if it was a mistake. You truly do have to fuck around to be able to find out. Yeah. Let's try. Oh, yeah, let's do everyday conversations. And then we hit this. We hit this. We hit this. Oh, it only has 8 steps at that point. Oh. And we still have a bunch of memory to spare. 32. 32. Let's see what it will take to the GPU. This will probably have 1 training step, right? 2 training steps. Okay, let's try loading that bigger data set again. Okay, let's reinitialize the model because we probably broke it a bit. And then we put the training configuration back. We recreate the SFT trainer. That's fine. And then we redo the training. And now we just wait. Okay, we're using 26 gigabytes of VRAM. That's good. We want to use a bunch of it. Okay, we have 92 training steps. That's probably good. But how long does it take to do each training step? We've done 2 training steps so far. And I think it needs a couple more in order for it to start to be able to estimate. So while that goes, I'll load Bikman 269. Does that do it? You gonna be able to do that, game? No, that should capture. Control FN, F11, F10, F12? Capture specific window. Why aren't you showing dolphin? Well, that's not gonna work. Okay, it's gonna basically take an hour because it has to do a bunch of thinking. But either way, like... Yeah, I see how this goes. Like... We free the so, like, while this goes, I'm gonna definitely not finish this on stream. I'm gonna let this run until it's finished. Then you can merge the LoRa into the base model. So when you use LoRa, you only train adapter weights while keeping the base model frozen. During training, you save only the lightweight adapter weights rather than a full model copy. For deployment, you might want to merge the adapters back in the base model for simplified deployment, better inference speed, and better compatibility with serving frameworks. So in order to merge it, what you do is you load the model, you load the LoRa onto the CPU, and then you merge it into the model on the GPU. Or you merge it in the model in the CPU. You put it to the output directory, you use safe serialization, aka safe tensors, and you have a maximum shard size of 2 gigabytes. And then use what you learned from the eCample notebook to load your trained LoRa adapter for inference. You free the stuff, you empty the cache, you load the model with the adapter, you make a pipeline for text generation, and then you do some inference testing. Okay. That makes sense. Let's read about prompt tuning while that goes. Prompt tuning is a parameter-efficient approach that modifies input representations rather than model weights. Unlike traditional fine-tuning that updates all model parameters, prompt tuning adds and optimizes a small set of trainable tokens while keeping the base model frozen. Unlike discrete text prompts, these soft prompts are learned through backpropagation while keeping the language model frozen. This method was introduced in The Power of Scale for Parameter-Efficient Prompt Tuning in 2021, which demonstrated that prompt tuning becomes more competitive with model fine-tuning as model size increases. Within the paper, at about 10 billion parameters, prompt tuning matches the performance of model fine-tuning while modifying only a few hundred parameters per task. It's like very, very small numbers. These soft prompts are contiguous vectors in the model's embedding space that get optimized during training. Unlike traditional discrete prompts that use natural language tokens, soft prompts have no inherent meaning, but learn to elicit the desired behavior from the frozen model through gradient descent. This technique is particularly effective for multitask scenarios, since each task requires storing a small prompt vector, typically a few hundred parameters, rather than a full model copy. What? Does it use, like... not language tokens to do this or something? Like, just tokens that are trained for the task, but when compared to other parameter efficient fine tuning methods, prompt tuning stands out for its efficiency. While low rank adaptation offers low parameter counts and memory usage but requires loading adapters for task switching, prompt tuning achieves even lower resource usage and enables immediate task switching. Full fine tuning demands significant resources and requires separate model copies for different tasks. Holy hell, parcel tugs for LLMs. Yeah, like, as this has been going on, it has been getting, like, less and less comprehensible. It's it's rough. I I assume that a lot of this is going to be a lot better with time. But yeah, this is a I did learn things here. Like, I don't mean to harp on the people that made this too much, but like, I actually have learned things here. I feel this is more fake tokens than a fake output of the encoding vector. That is the only thing I can guess what you just read. Yeah, like, having to guess what they mean is not a fun time. Let's just look over the section about vision models. Like, let's just look over this. Vision language models process image inputs alongside text to enable tasks like image captioning, visual question and answering, and multimodal reasoning. For the record, vision language models have beat optical character recognition at, like, the tasks that you'd use optical character recognition for, like reading text off of pages, like all that. It's they are superhuman at a lot of those things, but then suffer things like prompt injection in the images, which is a really fun, like, just thing to have to defend against. A typical visual vision language model architecture consists of an image coder encoder to extract visual features, a projection layer to align visual and textual representations, and a language model to process or generate text. This allows the model to establish connections between visual elements and language concepts. Vision language models can be used in different configurations depending on the use case. Base models handle general vision language tasks, while chat optimized variants support conversational interactions. Some models include additional components for grounding predictions in visual evidence or specializing in specific tasks like object detection. For more on the technicality and use of vision language models, refer to the vision language model usage page. Fine-tuning a vision language model involves adapting a pre-trained model to perform specific tasks or to operate efficiently on a particular dataset. The process can follow methodologies such as supervised fine-tuning, preference optimization, or a hybrid approach that combines both as introduced in modules 1 and 2. While the core tools and techniques remain similar to those used for large language models, fine-tuning vision language models requires additional focus on data representation and preparation for images. I'm gonna kill this. I learned what I needed to out of that LoRa thing. This ensures the model effectively integrates and processes both the visual and textual data for optimal performance. Given that the example demo model, Smol VLM, is significantly larger than the language model used in the previous module, it's essential to explore methods for efficient fine-tuning. Techniques like quantization and parameter-efficient fine-tuning can help make the process more accessible and cost-effective, allowing more users to experiment with the model. For detailed guidance on fine-tuning vision language models, visit the fine-tuning page. Visual. Oh no, they have a different acronym here. Vision language models bridge the gap between images and text, enabling tasks like generating image captions, answering questions based on visuals, or understanding the relationship between textual and visual data. Their architecture is designed to process both modalities seamlessly. They combine image processing components with text generation models to achieve a unified understanding. The primary elements of their architecture are an image goes into a vision encoder through some hidden states, through some modality prediction and pooling, and that gets put into a large language model, and so does the text. Image encoder translates raw images into compact numerical representations. Pre-trained encoders such as clip or vision transformers are commonly used. Embedding projector maps image features into a space compatible with textual embeddings, often using dense layers or linear transformations. Text encoder acts as the language generation component, translating fused multimodal information into coherent text. Examples include generative text models like Llama or Vicuna. A multimodal projector provides an additional layer to blend image and text representations. It is critical for models like Lava to establish stronger connections between the two modalities. Most vision language models leverage pre-trained image encoders and text decoders and align them through additional fine-tuning on paired image-text datasets. This approach makes training efficient while allowing the models to generalize effectively. So the usage is you take a user question with an image, you get the role user, you have the content is the image and the text. The vision language model does its thing. Assistant generates text content, and the LLM gives an answer. Vision language models are applied to a range of multimodal tasks. Their adaptability allows them to perform in diverse domains with varying levels of fine-tuning. You can generate descriptions for images. You can answer questions about the content of an image. You can find corresponding text for a given image or vice versa. You can assist in design, art generation, or creating engaging multimedia content. So the things that they are suggesting you use it for are object localization, like is one cat behind the other? Yes, one cat is behind the other in the image. The cat in the back is facing the camera, while the cat in front of it is facing away from the camera. You have zero-shot segmentation for looking for striped cats and it just highlighting it in the image. You have zero-shot visual question and answer. What is the breed of the cat? And the model would say, the cats in the image appear to be domestic short-hair cats. And then you have one-shot learning with instructions. So a shot in AI terms is an example. So, like, in this case, it says striped cats are called tabby cats. What is the breed of cats in the image? So what it's doing is it's front-loading the fact that a cat that has stripes is called a tabby cat. Given that a cat with stripes is called a tabby cat, what is the breed of the cats in the image? And if you look at the image, the cat has stripes. So with that context, the model says the cats in the image are tabby cats. Tabby cats are a common domestic cat breed and are characterized by their distinctive coat pattern, stripes on their body, and a ringed tail. Training and fine-tuning vision language models depend on high-quality datasets that pair images with text annotations. Tools like Hugging Face's Transformers library provide convenient access to pre-trained vision language models and streamlined workflows for custom fine-tuning. Many vision language models are structured to interact in a chatbot-like manner, enhancing usability. This format includes a system message that sets the role or context for the model, user queries that combine text and images, and assistant responses that provide text output derived from multimodal analysis. This conversational structure is intuitive and aligns with user expectations, especially for interactive applications like customer service or educational tools. Here's an example of how the input might work. So you have the system message, which just has a text component. You have the user message, which has an image component and a text component. Then you have the assistant response that gives the answer. Vision language models can also process multiple images or even videos by adapting the infrastructure to accommodate sequential or parallel visual inputs. For videos, frames can be extracted and processed in individual images while maintaining temporal order. Okay, Let's try the vision language model example usage. I have an ad coming up in 2 minutes. I can't delay it. I am not using a GPU. I need a GPU. Let's get an A100. Or actually, let's go with an L4. This notebook demonstrates how to use the Hugging Face Smol VLM Instruct 4-bit quantized model for various multimodal tasks. Okay. So let's install some crap. We're downloading things like Spooky Hash. Okay, that worked. Oh, I missed a chat message. That's just like me for real, for real. I also process image inputs alongside text to enable tasks like image captioning. Yeah, that's a mood. So then we import Torch. We import the image class from the Python imaging library. We import auto processor, auto model for vision to sequence, bits and bytes config, and we import the load image function. So I'm going to hit play here, and then we're going to download the Smol VLM instruct model, and we're going to load it in 4 bits. And the processor is the autoprocessor.from pretrained for Smol VLM instruct, whatever that means. So we're just grabbing a giant blob of data. Let's see how big Smol VLM instruct is while this goes. Smol VLM instruct is a 2.25 billion parameter model. And the download is about 4.5 gigabytes, so that adds up roughly. 2.25 gigabytes times 2. Yeah. 2.25 billion parameters times 2, that's about 4.5 gigs. That sounds right. So now we just wait. And then we're going to load some images. So we have these two kids holding hands and walking in the autumn leaves. And we have a present in front of a fireplace. That makes sense. Oh, I don't think we need to run that. Okay. Oh, we do need to run that. Okay. Just hit this button. Come on. Oh, right. It's still downloading things. The bars are green, so that's good. And then we set those variables. And then we load one image. We create the input messages. We prepare the inputs. We generate the outputs and print the result. So I hit the button. We load the image, we create the input, and then now we generate the output and we print the result. It says, image, can you describe the image? The image is the scene of a person walking in a forest. The person is wearing a coat and a cap. The person is holding the hand of another person. The person is walking on the path. The path is covered with dry leaves. The background of the image is a forest with trees. So now if we load both images, we have the second image loaded. We have our messages. The user says, There's two image contents, and we prepare the inputs by applying the chat template. We process that by adding the images into the embedding space of the prompt. We put the inputs to the GPU. We ask the model to generate up to 500 tokens. And the model, the user says, "Can you describe the two images?" The first image shows a child wearing a red hat and holding a red hat in front of a fireplace. The second image shows a present with a pine cone and a Christmas decoration. And processing videos is blank. Because why wouldn't it be? Either way, I get the idea. Some of the inputs are text, some of the inputs are images. It makes sense. I wonder what curse stuff could be done here, like connect the vision language model to a music generation model, then fine-tune with pairs of images and music. Like taking music, YouTube video music thumbnails to the songs contained within. That would be cursed. I've been thinking about doing something like that, but I have none of the technical ability to execute on it. Yeah. I also think I'm probably reaching the limit of where this course is going to be useful. So I think I might call it a stream. This was good though. Like, I learned things. Some things more useful than others. I have some bugs to. I have some patches to make to this thing, and I had a good time. I just really wonder what their synthetic datasets thing is going to be like. Oh, they have a PR for it. I guess that synthetic data generation can get expensive fast. Like, just not only like computationally expensive, but like just expensive. Before we call it quits, let's just look over this fine tuning a vision language model uh, notebook. So you use the dataset for a training run, use the fine-tuned model to generate a response and improve upon the base example. You try out the other datasets and show their improvement. Okay. You define the chart QA dataset. You show the structure of a single sample. Oh, a sample as in like the dataset, right? Okay. You pre-process it. Oh, and that like grabs the chart image or something. Okay, yeah, that makes sense. Then you set up a LoRa, you configure the trainer. You configure the trainer more, you initialize it, you train it, you're done. And I guess the other stuff is like you have to draw the rest of the owl and like implement stuff in the notebook. That makes sense. And looking over this, it's mostly like how to use the different types of training that they covered in earlier sections and saying like, hey, you're gonna want to use a LoRa for this because like this is really complicated stuff. Let's add a capstone project. Some students have asked for a capstone project that allows them to try their skills and get collective feedback on their work. That makes sense. Ah, yes, I have. I ran into this on stream today. Which version of TRL should I use? Yeah, like, I think this is a good stream. I hope y'all enjoyed this. Just some really chill music while we look into the unrestrained madness that is AI. Very chill. Yeah. That's what I wanted. I wanted just like laid back, cozy, just vibe core. But yeah, thanks for watching. Who should I raid? Is that one nerd live? Oh, that one nerd is live. I'm gonna raid Lithium Fox. Let's make sure he's on. Yes. Doing some racing in VR. There you go. And have a good day, all. Stay safe.